For today's warm-up, we are going to be working out of your classwork packet. So if you could please open your yellow classwork packet to page 38. Together we will be doing problem 1, which happens to be the longest problem, and then you will be doing the rest of the classwork on your own. You will need a calculator for the warm-up and for the rest of the problems today. Now most of the problems involve a calculator, but there are a few problems that say no calculator. If the problem says no calculator, please do not use a calculator. On Wednesday's quiz and on your test, there's going to be a no calculator portion, so you want to practice that now. So for problem 1, it says the half-life of rubidium-87 is about 48.8 billion years. A. Determine the value of K and the equation of decay for rubidium-87. So the first thing that we need to determine is which equation are we using? Is this a continuous decay or is it non-continuous? Well, we're told to determine K. And we're also talking about half-life. If we have this element rubidium, it's going to be decaying constantly, not decaying after a certain amount of time. So this is the continuous equation. So we're going to use y equals Pe to the power kt. Now, if you remember from the video, P is your starting amount. It didn't tell us how much we started with, so we get to choose. I generally like to start with 100, so let's start with 100 grams. So I have 100 e to the k. Now I know that I'm solving for k. I'm only permitted to have one unknown in the equation if I want to solve for k, which means I need to know y and I need to know t. Well, we're told that this is half-life. Half-life gives us a time after which only half of the amount remains. So if I start with 100 grams, that means half is going to remain, so 50 remains. So 50 is what we put in for y. Then we know that the half-life is 48.8 billion years. So for t, we're going to use 48.8. So what we need to remember then is we mean t to be billions of years. Okay, so now we need to solve for k. The first thing that I'm going to do is divide by 100. So I get 1/2 equals e to the power k times 48.8. Okay, so this is an exponential equation. At this point, I need to solve for k. If you look at that blue sheet, the blue cardstock that I gave you last week, that gives you some kind of hints and tricks. Anytime that you have an exponential equation, you're going to look at, can we rewrite the bases? So on the right side of the equation, we have e to some power. On the left side, is it possible to write 1/2 as e to some power? Well, no, it's not. So if we can't rewrite the bases, let's try switching this into log form. So this is going to be log base e of 1/2 equals k times 48.8. Now, nobody writes log base e, they write natural log, so really this is natural log of 1/2 equals 48.8 times k. That tells us that k equals the natural log of 1/2 divided by 48.8. If you do that in your calculator, you get k to be about negative 0.0142. Okay, so first thing you need to ask yourself is, does this make sense? Well, yes, it should. This is decay, which means that your k value has to be less than 0. It has to be negative. So this should make sense. If you remember from the video, I want you to store this as x. The way in your calculator to do this is do your natural log of 1/2 divided by 48.8. Once you hit enter, you should get the same k value I did. You then hit the store button and then the x and hit enter. Again, that store is the bottom right and then x is in the top left. You want to store that x value so that you can use it later. Before we move on to part B, we still have to write our equation of decay. So our equation of decay is y equals Pe to the negative 0.0142t. And here t is billions of years. So we're going to use this for the rest of the problem. So B, a specimen currently contains 50 milligrams of rubidium-87. How long will it take the specimen to decay to only 18 milligrams of rubidium? So let's start with our original equation, which is y equals Pe to the negative 0.0142t. Okay, so it says I currently have 50 milligrams, so that's going to go in for my P. So I have 50 e to the negative 0.0142 t. Now the question is, how long will it take? So that tells us that we're looking for t. I want to know after how much time it's going to have 18, so the 18 goes here. So now we have to solve for t. At this point, you're going to divide by 50. So you get 0.36 equals e to the negative 0.0142 t. Okay, so at this point I have an exponential equation. I can't rewrite either side, so I have to change this to log form. So this becomes the natural log of 0.36 equals negative 0.0142 t. That means that t equals natural log of 0.36 divided by negative 0.0142. Now remember, that's the value that we stored as x. So you actually want to do natural log of 0.36 divided by x. That x value is the same upper left x. So on the calculator, that is. So when you do that, you get your t to be about 71.93. And remember, it's not years. We defined t in part A as billions of years. So it's 71.93 billion years. Okay, it's really important that you store that k value as x, because if you don't, your answer could be a lot different from mine, just because of rounding errors. So now we're going to go on to C. C, if the specimen starts with 100 milligrams, how many milligrams of rubidium-87 will be left after 800 million years? So let's start with the equation that we found, which is y equals Pe to the negative 0.0142 t, but of course remember that that's the value that we stored as x. So now let's put in what we have. It says we start with 100 milligrams, so that's 100 e to the negative 0.0142. And then it says how many milligrams will be left after a certain time. So that means we're solving for y. Now here's the trickiest part. So it says after 800 million years. Remember that our t is in terms of billions of years, not millions of years. So what you have to do is you have to take that 800 million, so that's this, and you have to divide it by a billion. So that's a 1 with 9 zeros behind it. If you do that, you're going to get 0.8. And you intuitively might have been able to tell that 800 million years is the same as 0.8 billion years. It's not quite a full billion. So that's what we're going to put in for t. Okay, so now this is really nice. This is almost solved for already. We have y on the left side of the equation. So you can just type this in to your calculator exactly as it appears. Now you need to make sure that you are very careful and that you use the value of x that we have stored. So in your calculator, the way this would look would be to go 100 e, which is the second division sign, to the power, and then make sure in parentheses you do x times 0.8. So it looks like we're going to end up with 98.87 milligrams. Which should make sense. If we start with 100 milligrams and we've only gone 800 million years, we should be pretty close to 100. Because remember, the half-life is 48.8 billion years. So in those terms, 800 million years is not very long. So then part D, how long will it take rubidium-87 to decay to 1/16 of the original amount? Okay, this is very similar to parts A and B, so we're just going to stop right there. I'm not going to do it over again. Your classwork today, you don't have to do the rest of 38 and 39, but you do have to do pages 40 to 43. This is going to be due on Wednesday. I will check it before the quiz. I will also check the video. On Schoology is the answer key to pages 40 to 43 and some hints on some of the problems that might get you tripped up. So if you have any questions, make sure you ask each other or go to Schoology and look at the hints that I've posted. If you need one more problem or some help with the calculator, I will post the warm-up from the orange packet also so that you can reference at home. If you have any questions that you can't figure out, please feel free to email me and I will answer them tomorrow. Best of luck on the ACT tomorrow. Please make sure that you bring a calculator that has batteries or that's charged, and that you bring an ID and you don't bring your cell phone and all the stuff like that. You do have a quiz on Wednesday, so make sure you prepare for that, and I will see you Wednesday.